44 usually, okay? So you have 44, more than 30, okay? So is it clear? So yeah. So, you know, your total grade, you start with 18, actually, you pass the exam with approximately 16 or 17, depends on the case. You pass the written exam. Then it goes to the homework, then it goes on the top of that, you know, the oral, in case you have the possibility to do it, okay? And then, you know, if you do the oral, you saturate it to 27. If you don't do the oral, no oral, you saturate it to 24, okay? And then the written makes 44, okay? So this is the written test. Now, given that, you might ask me, where is the trick? Okay? Because, you know, in principle, I give you a lot of marks, right? To just reach 24. So come on, 24 is just even less than half. So, okay? Now, the trick is that you have 2 hours and 30 minutes. So, when you have a lot of exercises, you are always not mature enough to choose what you know what to solve. Because you are used to solve exercises one after the other. Now you have to choose. So you have to be very cool. You know what means cool? Okay? Okay? You should be very cool to choose the exercises that you can solve by just reading a few lines. So you need to say, okay, this is no, cannot. I'm not very good on that. Skip it. You see, you have this option. So this is, you know, something that is for you. Okay. So the difficulty I recall again is the time. Okay. Because if you have an infinite time, you can do everything. Okay. So, but you know, you are not paid in your future life. You are not paid to do everything with an infinite time, because you're paid to do, you know, as much as possible with a limited time. Okay? So that's a life, you know. So anyway, this is just a refresher. So someone was asking me, how is the exam? Okay, so in the meantime, I will tell you. Okay, so one piece after the other.
Very quick question. Is it possible to solve all the exercises, some parts?
Okay,
it's like
yes.
not completing.
You have in total, the 44, there are exercises 1, 2, 3, 4, 5, and 6. There are 6 exercises. These exercise number 1 is the basics. Okay, what we do today. Okay, so the basics means, you know, the most elementary part, something that you are using in the next. Okay, so I expect that everybody does the basics. Because it's an easy one. It's like, you know, started running, so warming up. Okay, that's the basic. Okay, so you get approximately, I don't know, 6 out of 44 or something like that. So you don't pass the exam with the basics only. Okay, is it clear? And by the way, just to conclude, to close the remark. Okay, I never seen anyone with 44. Okay. So the best, you know, is around 35, 37. These are the best I've seen. 39, okay? Just to give you an idea. So because of the time. If I extend the time to 3 hours, then, you know, the people start doing this, okay?
Oh, sorry. Do you get question marks for like every question, or do you?
No, I usually, you know, I give you. During the exam, I write some numbers, approximately the balance. Remember, the balance is depending on time. Okay? So if you have a part, if you have an exercise that is time consuming, that one perhaps, just to give an idea, okay, that one perhaps has 12. If one exercise is quick, okay, that one perhaps has 8. Okay, just to give you a number. So when I give you the exercise, you know approximately the level of difficulty or the time. Actually, it's the time. It's not difficulty. It's the time. Okay. And the question starts with easy, and then gets harder, harder, harder. Okay. So in every exercises there are several points. Point 1, 2, 3, 4, 5, 6. You see? Okay, so if you feel good on the topic, but not very strong, so you start solving 1, 2, 3, then you say, okay, I move to another one. See? But if you feel very strong, that's your topic. Then you're better to try to go deeper on that. Okay? But remember, this way of doing exam will be a trouble for a lot of you. Okay? Because I require your maturity. Okay? So you need to be self-critical. You need to be critical about, to be very critical, to know what are the topics you know better. And you do that. You see? I know this exercise. Okay, I do it. By the way, don't try to make the match of the exercise with the previous years. Forget about that. Okay? Forget. This is not the first year of the university where, the exams are more or less a photocopy of the others. Okay? Here they seem a photocopy, but they seem makes the difference. Okay? So
what's the difference between 31 and 39?
Nothing. 31, 39, nothing. But I prefer to see 39 because when I don't know if to give 30 or 30 lode, okay? But when I see 39, then my attitude is more okay. So, it's always true in the life. Try to leave good impression always, whatever you do. Okay, exams and so on. Okay. So because one day this will be back, will return to you as a benefit. So
when is the midterm exam?
I need to see it. Right? Approximately November, half November, approximately. Okay, that will be on Saturday because there is no other rooms. Saturday morning. Okay. Anyway, okay, so let's make our refresh about, the Z transform. Now, what I'm discussing here is well known to the telecom, and it might be first time you see for others, okay? So I try to balance the discussion. And then, based on the Z transform, we do exercises right away, because that is on the basics part, okay? Now, what is a Z transform? By the way, I took it from the appendix B, so it's an appendix, which for me means it's something that you are supposed to know. But if you don't know, I make a refresh. Okay, so that's the. And by the way, I make a refresh for what is necessary for us. So I don't make a refresh about how to design a filter, because filter design is another course. Okay. So I make a refresh for what is necessary for us. And mostly, what is necessary is what is the meaning of filtering. Okay, so how do I filter? Now, let's start, okay? So I want to keep it quite short, so I don't want to spend more than 30, 40 minutes on that. Okay, but if there are people never seen, how many never seen the Z transform in life? 1, 2, okay. Now, in case you have trouble, in case that is too quick, okay, do this way. Perhaps you come to me after, and we can see some details. Okay. So otherwise, I don't want to slow down all the others for just you two. If you are really in trouble, we can meet tomorrow. If you have an empty slot, and we can discuss. So I can make you a private discussion on that. Okay. Not all, so it's a matter of 3, 4, 5 at the most. Now, what is a Z transform? Z transform is a very smart idea, okay? Which is, the Z transform is to represent a sequence. A sequence is a set of samples, okay? So a signal is a set of samples. So when I indicate these, I have a signal like this. This signal itself, if I zoom in, it is represented by a set of samples. And samples, you know, are simply indexed by a number which is, I don't know, it's 1, 2, 3, blah, blah, okay? And the value. So that one is x1. This one is x2, and so forth, okay? So that one is a set of samples which, you know, are indicated as xn, okay? So this xn is the set of samples representing a discrete time signal, okay? So I call this one as a signal. Other discipline, they call it time series, because it's a series of time samples, like the Apple stocks. The file of Apple stock is a time series, because, you know, every value is referred to a specific time. But, you know, if I just index 1, 2, 3, 4, 5, blah, blah, those are time samples, okay? Now, so now I have a set of samples which is xn, and now when I indicate in this way, this one, I indicate that it's a total set of samples. Now these samples can go from minus infinity to plus infinity. But, you know, if I consider a limited set of samples, like samples that go from 1 to 10, then, you know, I still indicate it as xn. Okay? So, you know, these set of samples can be represented. Please look at the word represented. So that one is a representation. Okay? So I represent in another way. Of course, you know, we are engineers, so we don't do anything if there is no value. And so this way of representing is very convenient for discrete time signals. And we will see in 1 minute for that. So I represented this set of samples by a polynomial. So the samples are the coefficient of the polynomial. Finish. That's it. So I simply represent, you know, a set of samples by coefficient of polynomial. So this coefficient has the ordering which is represented by the power of every index. Okay? So that means that if I have 2 samples, just to still be, you know, trivial, if I have 2 samples, which is, I don't know, A, so I have a sample in position 0, that is A, and a sample in position 1, that is B, okay. So that one is the polynomial representation makes that this one is x0, that one is x1. So if I write using the definition, that one is x0 times v to the minus power 0 plus x1 z to the power of minus 1. That's it. Okay? So when I indicate, and by the way, this one makes 1. Okay? So when I indicate in this way, that one is x0 plus x1 z to the minus 1, which is by the numerical value, I indicate just a and b, so it is a plus b z to the minus 1. So which means every time I have z to the minus 1, the coefficient is the amplitude of the sample at the position of delay, 1, okay? Because, you know, 1 is the corresponding delay of the sample. You know, if I consider, I don't know, a value in z to the minus 2, is the position of the sample in, you know, is the value of the sample in position 2 with the delay 2, and so forth, okay? So now, given that, you know, this similarity, okay, so I indicate using this notation. So I indicate with x, capital X. It's not a matrix, it's just a capital, okay? Capital X of argument z, which is a z transform, so I indicate with just calligraphic z, is a z transform of the sequence xn, okay? Which in formula means just the sum of the series of all the coefficients of the polynomial in z. Now, the inverse of the z transform I indicate in this way, which is z to the minus 1 of the z transform, and analytic is computed this way. Now, in my life, I computed this way, I think, a couple of times, 2 or 3 times. So it's a nice formula, but, you know, I've never used. Okay, I use the most typical one. And now you will see why. So anyway, but you know, since there is this integral, okay, which is along the circle, okay, this circle should include the origin, so the 0, okay, technically. Now let's see why. Why z transform? You know, the z transform, okay, and by the way, since that one is a polynomial, so it's a polynomial, you know, power of the polynomial depends on log, okay? So if I have a polynomial of order n, that means that I have an n plus 1 samples, okay? So let's look at it, for instance, okay? So that means that this polynomial, we know that has zeros, okay? So the zeros of the polynomial are those values such that the polynomial goes to 0, okay? So suppose that these zeros of the polynomial are indicated as zk. So zk is the k0 of the polynomial xz. Okay? So now you know the fundamental theorem of algebra says that if I have a polynomial of order n, that one contains n roots. Okay? So I can write, you know, this polynomial. And then assume that my polynomial, so what is a polynomial of order n? The polynomial of order n means, just to exemplify, so it is xz equal to x0 plus x1. x1 has a delay minus 1, so z to the minus 1, plus x2, z to the minus 2, plus x and z to the minus n. Okay. Now the reason why there is this minus, okay, is because it's a conventional way. Okay, it's due to the conventional notation. So this one is a polynomial of order n, and this is the coefficient of the nth term, okay, the last term. So I can take this polynomial, you know, if I count how many entries, so it has a 0, 1, 2, 3, blah, blah, and then this has n plus 1 entry value, okay? So that is the nth order polynomial, which corresponds to a sequence of n plus 1 samples. Because that is 1, 2, 3, 4, blah, blah, and then it's n plus 1, okay? So that means that rather than representing these sequence, you know, I might represent this sequence as, you know, I have a sample is 0, 1, 2, and then it is n, okay, which in total is n plus 1 samples. Rather than representing this way, I represent by a polynomial. Now, we know from the theorem of algebra that any nth order polynomial has any nth order polynomial has n zeros, okay? Now, the zeros can be, you know, with a different multiplicity, but you know, multiplicity means coincident. So, but let's assume that all the zeros are, I mean, distinct, which means, you know, they are not, their multiplicity is 1. So I can write the polynomial now by a product of all the roots. Okay? So if I multiply all these roots with this product, I get the original polynomial. So this one is a 0. Now, a very simple proof, if I take a zk and I put a zk in place of the z, I get 1, and I have 1 minus 1 gets 0. Okay? Now, a polynomial is called the minimum phase polynomial if the roots are all inside in a unit circle. And the polynomial is called the maximum phase is if all the roots are outside of the unit circle. There is a reason for that, but you know, in case all the others should know, and so for you we can discuss. Okay? So, but you know, take it as a definition. So I simply take this polynomial, okay, and then I write roots in MATLAB, and I get the value of the roots. That's it. So I look at the absolute value, and if the absolute value of all the roots are inside the circle, which means, you know, are lower than 1, then the polynomial is minimum phase. If it is larger than 1, it's maximum phase. If it is, you know, it's some of lower, some larger, you know, is a mixed phase. Okay. Now, there is you know, there is this. By the way, the sequencer can be real and complex. Okay, so you know we can look at complex. But now there is just a notation aspect. Okay, how I write complex. Okay. Now, you know, this is a remark on notation. Now, when I write x star, so when I write the star here, okay, this means that I take the complex conjugate of the coefficient of the polynomial. So all the samples are complex conjugate when I indicate it this way. If you go to other books, they use a different notation, okay? But you know, I mean, this one is much more convenient to describe the set of possible operations that we will see later. So, which means that if I take the polynomial and calculate the complex conjugate of the polynomial, which means I take it this way, so I take the sequence and compute the complex conjugate. Since the complex conjugate goes into x and z, and since z is complex, this is totally different from that, where when I apply the complex conjugate is only on the coefficient. Okay? So keep in mind about that, because there is a set of books that use this notation to indicate, you know, the complex conjugate. Okay? I will use this one. Now, I told you it's useful. So useful for what? Okay? It's useful because, you know, when I make the convolution, okay, now this one is the sum of convolution. So when I make the convolution between two different signals, if you like, okay? Now I use the sum of convolution, you know, the sum of convolution. So I have hk and then I have x and minus k. Okay. By the way, when I write the sum on k, means summing all the k that are different from 0. Okay? So I'm not writing, you know, goes between minus infinity to plus infinity. And if, for instance, if hk has a support, which means as an interval where it's different from 0, this one extends to the support of h. If x is different from 0 between a certain interval, this sum is applying only to different from 0 terms. Okay? So I'm not writing, I mean, since we will write a lot of sum, so I'm not writing the extreme of the sum, unless it's not strictly necessary, okay? Which will be very, very rarely. Now, okay, this is, you know, the permutation property between convolution, so that is x convolved k, h, and this is h convolved x, you know, which is flipping. Now, the good news is the following property. Property of convolution. If I have a convolution, the convolution can be written as the product of the z transform, which means it's the product of the coefficient of the polynomial. Okay? So that's important property. Now, so let's use this property where, you know, when I have a product of z transform, that is a convolution. So let's keep in mind about this. Okay? Every time we have a product, it's a convolution. Now, let's make, you know, let's consider the factorization that we described before. So before I said, if I have a certain sequence with a certain length, I can decompose into the product of the roots. Okay, so these are the roots. Okay. But now, you know, if I look at the inner meaning of 1 minus z to the 1, z1, z to the minus 1, that one is a sequence of two numbers. The first number is 1, the second one is minus z1. So, you know, that means that since a product is a convolution, since the product between these two should be a convolution then. And the convolution that I indicate is this way. So this is a convolution between, you know, the first coefficient is 1, delay 0, and the second coefficient is minus z1 delay 1. Convolve with, with the first coefficient in 1, in 0, and the second coefficient that I know is minus z2 at the delay 1. So I convolve monic forms, which is, is a sequence of two numbers. And by the way, out of the two numbers, one is 1. So the first is 1. Okay? So that is a convolution. So that means that this sequence is the most elementary sequence. So every complicated signal can be written as a convolution of these two sample signals. So probably you remember by the analysis, okay, or the calculus, that if I can write a property on two sample signal, on the most elementary signal, if the property is linear, it applies to 4. Okay, and this is the same. Now, okay, which is I indicated. Now, so that another remark. It is customary to use z to the minus 1 as a unit delay operator. Okay. So now it is very common to write it this way. Suppose that I have xn, and I take this one, okay, and I filter by a filter z to the minus 1. Now this means that if I write this way, it is like if all the sequence input will be multiplied by z to the minus 1. Now this multiplication, it is a common practice to make this multiplication as an operator of a unit delay. Okay, so which means that the sequence is xn minus 1. So it's a delay by one sample. By extension, if I chain, so if I put the sequence of delays, z to the minus 1, z to the minus 1, z to the minus 1, okay? So the polynomial, I have z to the minus 1 times z to the minus 1 times z to the minus 1 makes z to the minus 3. Okay? And this is a delay of 3 samples. So that one is x and minus 3. Which means all the sequence is shifted as a delay by 3 samples. Now, once again, so that is on the definition. So this is typical on the description, okay, as indicated here. It is typical of the description by block diagram. This is a block diagram where we highlight the function of delay from the function of multiplication. Now, there is one remark I make it. If I take a sequence x1 minus z is the same as xz, except by reflection with respect to the mirror. Because, it's like to count the samples that they go, it's z to the minus 1, z to the minus 2, z to the minus 3. If I make a z1, z2, z3, that means that the samples are counted on the other way. Okay? So, this way. Very easy. Okay? So, if I take a sequence, I don't know, I make x0, then I have x1 in delay 1, and then I make x2 at delay 2, and this is xz. If I make x1 over z, the sequence is x0, 0, x in position minus 1, there is that value, and I don't know, it's in position minus 2 is x2. Okay, so which means I'm flipping the vector, from the around the origin. Okay, so if I make x1 to z means flipping. Okay, which in MATLAB is made by flip ud. If you take a vector and make a flip ud, then the vector is, it's flipped. Okay, you reverse. Now, when I write the z transform, Okay? And you know, I can calculate, when I indicate the z transform, I can calculate the sum of the polynomials. So in some cases, this is summing to a finite value. Now, this is summing, it has a limit. So I have a specific value that constrains this sum to be valid. Let's make an example. Assume that, you know, with a common z transform, yeah. So we will say the common z transform. So let's assume that, you know, I have a set of samples. These set of samples are a n, u n. Now un is a step function, okay, which is, you know, it's different from 0 only for value that is larger than 0. Okay, so this set of samples is a set of samples. So it is a to the power of 0 is 1. Then I have a in position 1, a square in position 2, a cubic in position 3, and so forth. Okay? So that one, you know, is an exponential, okay? But since an exponential is only for n larger or equal to 0, this is called the causal exponential. Okay? Now, when I say causal, means that this exponential is only for numbers that are positive or 0, from 0, 1, 2, 3, so on. Okay? Now, you know, I take this series, I take the z transform, and the z transform is, you know, is a sum for all the value larger or equal to 0 of a n z minus n. Now, the sum of this series, okay, is 1 divided by 1 minus a z to the minus 1. Now, this sum is possible only and only if the argument of the power n is smaller than 1 in absolute value. So I can write that, you know, this one is valid, okay, only if, provided that, okay, that the absolute value is smaller than 1. And this means that, you know, it is only true for z, absolute value of z, larger than the absolute value of a. Okay? Now, this one, you know, is defining the so-called region of convergence. So I can sketch this region of convergence. Okay, so that one. And you know, since it says that if this one, okay, I indicate in this axis as the real part of z and the imaginary part of z, and then, you know, this value is a. Okay, a can be complex, doesn't need to be real. Okay, so the number a. So I copy it. I say, okay, so this region of convergence, I copy it. Okay, is only if the absolute value of z is larger than the absolute value of a. Okay, so this is the absolute value of a. Okay, so the region of convergence is only if we are outside that. Okay. So that is the region of convergence. Now, the roots, okay, now we will go back to that. The roots on the denominator, you see the other root now. Okay, so here I have a lot of roots in the numerator because these are the zeros. Now the roots of the denominator are called pole. So a pole is a root in the denominator of the signal in case the sum of the series exists. Okay. Now, a sequence is not a filter. Any sequence is causally stable in case it is not diverging. Okay. Now, this property, okay, says that, this exponential is causal because that is the only possibility to exist. Because the anti-causal exponential will be exploding. Because the anti-causal exponential does not fulfill that condition. So it's divergent. Okay? So I never seen a system which is divergent unless it's exploding. Okay? So since we don't want exploding signal, we will handle all converging signals. Okay? Now, in if there is a Fourier transform equivalent if all the poles are inside his or are inside the unit circle. Okay, that's another condition. In other words, the region for convergence should include should disable. Okay, so the region for convergence should include the radius 1. Okay, so if the region of convergence includes the radius 1, okay, now if the region of convergence comprehends the absolute value of z equal 1, then it exists the Fourier transform of the sequence x. And now we pay a little bit of attention to that. Okay. Now, one more. Let's take another sequence. Now, the sequence that I'm discussing is reversing time. So it's Bn, Un minus 1. Okay, so these sequence, okay, start from 1, minus 2, minus 3, and so on. Okay, so it's a sequence which is going the other direction. So, 0. So, B squared, B cubic. But since it is reversing time, okay, so that one, is minus 3, minus 2, minus 1. Okay. Now, this is the sequence of reversing time. Okay. Now, if I have this sequence, which is reversing time, is exponential, but is anti-causal. So, if I compare with the other, where is it? With the other, okay, which is going in this direction, this one is going on the other direction. Okay. So that one, now is an anti-causal. Now, anti-causal means that, it exists for negative value. It's anti-causal and then it's an exponential. Remember, when I write anti-causal means that, the axis goes in the other direction. Now, why should I take the anti-causal and should I specify anti-causal? Because if I don't specify anti-causal, this one diverge. And nobody handle exploding signals. Okay? So mathematically is a singularity and you don't treat a singularity. We are engineers, so we say it's not, we don't treat exploding signals. Okay? So we skip the analytical part. Okay, so I can write, similarly, I can write a z transform. So when I write a z transform, I use a definition, okay? So it is, it is on minus 1, it is b to the minus 1. b to the minus 1, becomes a b, okay? So I can reverse the axis. So I take, I just change the sign, okay? I make the sum positive. When I make the sum positive, I should remove, because that sum is summing from 0, okay? So here, the 0 does not exist. Okay, so since here 0 does not exist, what I do is I sum from 0 to infinite, and then I take out this value, and this one is representative of b to the power of 0, and then z to the power of 0, which is 1. Okay, so I sum and subtract the 1. Okay, Then the sum of the series, look, I mean, it's very similar to the other. And this one has, you know, as a pole, and as a pole in B. And so in order to converge, you know, I need to have these, the region of convergence should have that the Z should be smaller than B. Okay? So now it depends where is B. Okay? So now if I sketch this one on the same plot, then now B might be here. And now you know the region for convergence says that these exist only if it is smaller than B. So I have the region for convergence that if I use both the signals at the same time, the region for convergence should contain an overlap part where, you know, it should have a common part. In this way, both signals might coexist. If it is not the case, they cannot coexist. Now, okay, let's move forward. Now, we can make a polynomial factorization. Now, up to now, you know, every telecom should say, okay, I mean, I know this story. Okay, now a little bit, something that is more subtle. Now, since, you know, any filtering, okay, any filtering is obtained by convolution. So if I have a system, any system, you know, is in some way filtering, okay? And by the way, let me have the page. So for instance, you know, most of the cases, if I have a signal xn, which is filtered by a filter which is represented by the z transform z, and the output is yn. Look at the notation. Xn is in time, hz is in the z transform, and yn is in time. Okay? Look at that. Perhaps, you know, you might have noticed that probably I could have written xn, and then I have hn, where hn is the impulse response, okay, and then I have yn. Now both notations are equivalent. Pragmatically, the beauty of notation is that it's a notation. It's a way to have people to speak the same language. Once we talk the same language, then we can move forward. In engineering, notation sometimes are very important. So try to be flexible on notation, otherwise you cannot talk with the others. Okay. It's like the delay. We write z to the -1, but if you talk with the people that make a coding, they call the delay with a positive power. Okay? And now you say, ooh, are they different? No, they are the same. Okay. So let's move forward. So you know, and yn is obtained by convolving. So I take xn, which is convolved by hn, which is convolving by the filter. Okay? Now I can write as yz, z transform of y is equal to xz multiplied by hz. Okay? Now, let me make a, you know, I said I want to make a digression of that. Okay? So, in many cases, a linear filter, there is a theorem which says that, a linear filter, okay, can be represented by a finite difference equation. What is a finite difference equation? A finite difference equation says that, you know, if I have a signal yn, okay, the output of a linear filter can be written as a sum of, with respect to k, of coefficient bk, okay, multiplied by x n minus k. Okay, this one is a convolution because I'm convolving b with x. Then I have minus a sum on L of A L, and then I have y n minus L. Now, what is this? This is the output. So that one is recycling the output into the together with input in order to get the output at time n. Okay. Now, this component is called a recursive component. Okay. And this one is non-recursive. Now this one is the finite difference. So any linear time invariant system can be represented by finite difference equation represented this way. Now let's apply the zeta form. Okay. So when I apply the zeta form, I apply the zeta form on the left and apply the zeta form on the right. Okay. So when I apply zeta form, you know, on the left it is yz equal. Now, when I apply the zeta form is on the time samples. Okay. So that is, you know, the zeta form. Okay, is bk. Then it is a delay of x by k, so it is z to the minus k, and then it is xz. Summing okay. Minus. By the way, sorry, I need to write L different from 0. Okay. Minus. Then that one is sum on L different from 0 of A L. Then I have z to the minus L. Then I have, you know, I have y, z transform of y. Let's make another step forward. So let's group on the left the y, because, you know, I like to write it this way. I like to have y on one side and x on the other. Okay? So if I group it this way, so I group, you know, y on the left and x on the right, what I get is the following. Yz is equal to the sum of k of bk z to the minus k divided by sum on L different from 0 ak. Let me shift a little bit up. One plus sum of L different from 0 AL z to the minus L. Okay, so I, you know, multiply by x z. Okay, so what does it mean, all this story? It means that, you know, what I indicate here this one is the same as that. So I can indicate any age z, any filtering, as a ratio between polynomials. There is a polynomial on the numerator and there is a polynomial on the denominator. The polynomial on the numerator is giving the roots of polynomial and numerator is giving the zeros of the system. The roots of the polynomial in the denominator is giving the pole of the system. Okay? So that is, you know, what I mean I'm used to say. Okay? So now this means let me add another page, okay, so that you have some development. So at the end of the story, what they did is yz can be written as b, the polynomial on the numerator divided by the polynomial on the denominator multiplied by xz. And this one is the filter hz. This is the filtering. Okay. This is the filter. So this filter, okay, is that I can take the sequence xn, and then I can filter by BZ on AZ, okay, which is equivalent, which gets YN, okay, which is equivalent to write a cascade of two systems, BZ 1 over AZ. This is, I don't know, this is X tilde VN, just to give a label, and this is Y. Okay? But I can swap the input. Okay? So I can swap the input, and then I can write in totally equivalent way, so that it's totally equivalent. This is Xn input, which is BZ 1 over AZ, and then is filtered by BZ. The output is still the same. In some cases, it's convenient to do one way. In other cases, it's convenient to do it the other way. Okay? It depends on the case. We will work a lot on that at a certain point, and I'm giving you time to digest all this before I start the random process. Now, let's look at a very special case. So now, given that this is the most general, okay, so this is the most general linear time invariant system. Okay, this is the most general. Now, a special case. A special case that is very useful. The special case is the following. Suppose now that I look at a case where BZ is equal to 1. Okay? So there is no 0. Now let's look at a case where what I can do is the following. That I have xn 1 over a z, and then I have yn. This is the special case that we are going to analyze. Now, what do we know about that? We know that an is a polynomial. Okay? An is a polynomial. So let's make another step forward. So since an, az, is a sequence, az is a polynomial, okay? So I can take the polynomial az and make it, so factorize the polynomial as a product of roots. These roots are poles, okay? So I factorize into roots. But these roots are poles. Okay? So I use the same rule. So I have 1 minus pole 1 z to the minus 1. Then I have 1 minus p to pole 2 z to the minus 1. It's a product, as I did. Okay? Now these poles can be inside and outside of the unit circle. So we know that so every single of that, okay, so that one over az can be written as 1 over 1 minus p1 z to the minus 1 times 1 over 1 minus p2 z to the minus 1 times blah blah blah. Clear? Okay? Now, so that means that it means that it is this one, what is the sequence? Convolve with the sequence, convolve with another. Okay, so it's a sequence of samples. Okay? Now magic. Now I go back and I look at the results. Now I copy the results here because I want, I want that you have to clear this concept, okay? Because otherwise you come to me and say it does not exist. It's a typical. So I use this result. Okay, that result means that if I have a pole, now I copy what I wrote with the only difference that rather than calling A, I call it P. Okay? So, which is, it's a minor difference. So I have that one, okay? So I say, if I have 1 minus P z to the minus 1, okay? And, this P as a region for convergence that is smaller than 1, okay? Then the sequence in time corresponds to an exponential. Okay? 0, 1, 2, 3. It's 1, p squared, p cubic, blah, blah, blah. Okay? I'm copying. Nothing new. I'm copying the other. I'm copying that. Okay? So that one says, if I have, let me call P1, just to distinguish. Okay? So this is P1 should be smaller than 1, then P1, P1, P1. Okay? Then, I take that one, and look at that. And look, it's 1 minus 1 divided by 1 minus b z to the minus 1. Okay? So, rather than calling b, I call p2. Okay? So, let me write it this way. Minus 1 minus p2 z to the minus 1. And my condition says that, b has to be larger than 1. So b now is p2, so p2 should be larger than 1. If this condition is met, as the case, then my response is an anti-causal exponential. Okay? So, which is, doesn't start from 0, so that here, and so forth. Okay? So I have a causal exponential, anti-causal exponential. Okay? So it's minus 1, but this is minus 1 is not important. Now, here, so, now let's go here. So now, we are now taking any arbitrary polynomial, right? So any arbitrary polynomial, as I wrote there, okay, can be written as a product. Now I have, imagine that P1 is this one, that P2 is this one, okay? Now some of you, since this P1, is internal to the unit circle, some of you say, okay, good, that one exists. But since P2 is larger than the unit circle, some of you say, or might say, that that one does not exist. Because the pole is outside of the unit circle. Now, so that means that we have two conditions. So I have, one pole which is P1 that stays inside of the unit circle, and I have a second pole which is P2 that is outside of the unit circle. This one is unitary circle. The radius is 1. And this one is real part of Z, and that one is imaginary part. Okay? So, remark, which is a common misunderstanding. A common misunderstanding for those, just to explain for those that they see the Zito's form for the first time. If you ask your colleague, and you say, okay, I have a pole outside of the circle, they say, it's impossible. It does not exist. Okay? It's not true. It is, it exists, but it's not causal. It's anti-causal. Was okay? Is it clear? So every time you have a pole outside of the circle, That one is anti-causal system. So that means that if I need to take that arbitrary polynomial, the impulse response of this system exists. It is composed by a causal part and anti-causal part. Okay? So, you know, if we go back to the point now, if P1 is smaller than 1 and P2 is larger than 1, okay, then this one corresponds to a causal system, causal sequence. And that one is anti-causal. Okay? Now, of course, if I convolve a causal with an anti-causal, it comes a sequence that has, you know, it has a support, so it takes a time between minus infinity to plus infinity. Of course. Now, you know, it might be complicated to be implemented. Okay? There is a way to implement as well. But you know, I mean, this is the rule. Now, similarly, I can separate, you know, all the poles that are inside the circle, all the poles that are outside the circle. But you know, what is a polynomial when all the roots are inside the circle? Minimum phase. What is a polynomial where all the roots are outside the circle? Maximum phase. So that means that this one can be written as a minimum phase, z, multiplied by 1 over a maximum phase, z. I indicate in this way as minimum phase, and that one is maximum phase. Okay? So, to conclude this part, which is, you know, is less stupid than you can imagine, because you make so many times a mistake here, okay? I would say any basics that I have, you know, sometimes there are mistakes or similar. Or even in the inner part of the exam, there are confusion about that, okay? So I want to make it now, so you have time to reflect, to think about that, okay? Meditate a little bit, and then dissipate any ambiguity. Because if you have an infinitesimal ambiguity, it comes out before or later. Okay? So this one means that it's this one is a causal sequence, and that one, okay. So the inverse Fourier transform, the inverse Z transform, and that one is anti-causal sequence. So now you understand this word. This word, which is, you know, I acknowledge that it's very compact, and so, you know, sometimes, I mean, if you know the topic, then it's obvious. Right? So that means that if I take a signal, this signal can be written as a pole, then it's very convenient to write as a minimum and maximum phase. And the minimum phase corresponds, you know, to a causal part and anti-causal part, which is indicated here, correspond cause, blah, 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 you can read by yourself. The same property holds for max and minimum phase zeros, same sort, okay? So that means that, you know, I mean, you can in principle decompose this sequence as any sequence into the ratio between polynomial and minimum phase and maximum phase. Depends on the case. Now, about this partitioning, this or that, okay, at a certain point, when we talk about processes, random processes, okay, you will get totally messy. So I make it now, so like I do this way. I throw a seed, I let you meditate and bounce into the brain, okay? And then when I do the process, I hope all the issue will be dissipated. This is a nice thing of making the class several years. Okay, now there are some properties, okay, you can look at, but you know, it's, if I make a complex conjugate, it's a complex conjugate, the irreversible sign, a delta, which is a delay 1, is 1, delay by n is e to the minus n, is linear, convolution, we already saw it, and these are other properties. Okay. Fourier transform. What is the Fourier transform of the sequence? Now, the Fourier transform of the sequence is nothing else than the Z transform when I read the Z transform along the circle. Okay. Now, let's see. So, let's take the definition of Fourier transform. The definition of Fourier transform, which I indicate in this way with this F, is a Fourier transform of the sequence. Remember, Fourier transform is not a discrete Fourier transform. We will see in a minute. It's different. They are not the same. Sometimes, you know, this is another issue where you make a confusion. Not necessarily in my class, but when you start working. When you start working, you make a mess between Fourier transform and discrete Fourier transform. Apparently, they seem the same for you, but they're different. Okay? So let's clarify now. So, you know, now the Fourier transform is the Z transform. If I look at the formula, you know, the formula on the Z transform says that is a sum. Let me write in blue, I prefer. This is the sum of Z transform of n of x and z to the minus n. If I look at the formula, the Z transform and the Fourier transform, the only difference is that I need to plug into the Z transform aj on. So what does it mean? It means nothing else that, you know, if I have a certain Z transform, I read, let me say, the Fourier transform by taking Z transform you know, and walk. So it's like if I'm sitting here and I walk along a unit circle. Okay, and the angle is exactly omega. Okay? So, you know, so I don't like to have the roots, possibly a pole in the unit circle, because I mean, otherwise a pole is bouncing down to the infinite. Okay. So that is some trick. Okay. Now, one comment more. Okay. Now this comment, you know, it's quite crucial for phase-only filters. Okay. If I take a sequence and I take the sequence where, you know, look at that. What is that? I have 1 minus zk z to the minus 1. This is the minimal sequence. One sample, two samples. 1 and z to the minus k. Now, let's make, you know, the complex conjugate and then the transpose. Okay. Sorry, the complex conjugate and mirroring. Okay, so reflecting. So we know that if we are reflecting, what we do is that, you know, we take x and then we have 1 over z. If we have 1 over z, means that if I have a sequence, it goes on the other side. That's why, you know, I did this trick. Okay. So now, if I make x a star, which means I make the complex conjugate for every coefficient, then flip. Now, what's happened on the pole? Or what happened on the singularity? On the singularity, it happens the following. If I do this operation, now I zoom it, so, you know, it stays on page. If I make this operation, means that if I have a unit circle, and I have a root that is located here, this is zk. Now, I draw bigger because that is too small for you when you print it. I'm making a new page. It's better. Okay. Now, if I write 1 minus zk z to the minus 1, and I make, this is x z, elementary. I make xk star, complex conjugate, 1 over z, okay, which is equal to 1 minus zk star z. That one is a sequence which is flipped. Okay? So the sequence number 1 is 1 and minus zk at the delay 1. The other is 1 and it is at the delay minus 1 is minus zk star. Okay. So, you know, I'm simply mirroring a quick complex conjugate. Now, if I do it this way and I compute the Fourier transform of both, the Fourier transform is the same. Which is, you know, it's very strange. So, if I compute the absolute value of x, k, z, when z is equal to aj omega, Fourier transform of the first is equal to the Fourier transform of the second one, where, you know, I'm computing x star 1 over z, where z equal aj omega. So, which means that, you know, by the absolute value, so by the amplitude of the Fourier transform, I cannot distinguish these as z, k, and the second pole is in z 1 over zk star. The first one is here. The second one is there. I cannot distinguish any singularity, which is any roots, if it is, you know, if it is taking the same sequence and I flip the sequence around the 0 and I make it a complex conjugate of every coefficient. I cannot distinguish by the Fourier transform the absolute value, because it contains just the difference in phase, not in amplitude. Okay? That's a property. Again, this is another property that we will use when we make the Pauli-Wiener decomposition of the power spectral density of the autocorrelation sequence. Okay. And okay, this is the concept which is indicated here. Now, and last, I told you, I said, okay, let's make a discrete Fourier transform. What is a discrete Fourier transform? Discrete Fourier transform is simply the Fourier transform evaluated by sampling the frequency regularly in omega. Okay? So let's read it. Now, the discrete Fourier transform is the Fourier transform evaluated along n frequency point uniformly spaced apart. Let's see. Sk is the kth coefficient of the discrete Fourier transform. Discrete Fourier transform is an operation, so, you know, you go to MATLAB, you write the DFT, and you get to the discrete Fourier transform. Okay? So what is a discrete Fourier transform? Is the Fourier transform x evaluated for omega equal 2 pi divided by nk. So it's regularly spaced in angle. Okay, that's a discrete Fourier transform. And this one, you know, is regularly obtained up to n samples, because, you know, I'm just calculating around the circle. Okay? So now that means that means that just for our friend that, you know, they didn't do this in before, that means that, you know, the Fourier transform is the z transform evaluated into the circle. So if I walk along the circle, this axis omega, okay? And so if I take any arbitrary point here, that angle is omega and the radius is 1. This is the Fourier transform. The discrete Fourier transform in red, okay, is the same, except that I know only these values. So the DFT in red is the sample Fourier transform on, on omega, okay, which is regularly on a certain number of points, okay. So the sample on over 2 pi divided by n multiplied by k. Okay, so this angle, is 0. This angle is for omega equal 2 pi divided by n. This angle, okay, is for 2 times 2 pi divided by n, and so forth. Okay. So the angle, the angle spacing of the Fourier transform, discrete Fourier transform is 2 pi divided by n. Okay. So because of this, once we have the discrete Fourier transform, we might have the Fourier transform, but it's only in some special cases where the Fourier transform is very smooth. Now, this refresh all. Now, we are ready to make the basics exercises. Took more than I imagined. Let me start with a very, I just give you an idea about the exercise and we make it after. I continue till 6:30 today, just so that you know. Now, these are the text of the exercise I choose for you. For instance, given a quadratic form, write the quadratic form in a matrix notation. Okay? Now, define what is a positive and definite quadratic form. Third question, find the minimum of f(xy) and its value at the minimum. So, let's make this one, because I choose this one as very easy, very simple one. This one is something that we can do in one line. Okay, so the text is this one, it's a quadratic form. So let's write the quadratic form by using matrices. That's an excellent way. Okay, so let's write f, rather than writing f(xy), okay, I can write f(x) and y. And that one, it's... Now, I need to write the quadratic form by using matrices. Okay, so if I need to use matrices, I know that the quadratic form, okay, is x and y, row vector, then there is a matrix, okay, then I know that it's x and y in column. So the first entry, is the term, the argument of a square, so it's 8. Then I have all the the diagonal, the other diagonal entry. Now, here, this term, the second one, what goes here, is a y squared. What is a y squared? 0. Now, what goes here? Here goes x, y. How much is x, y? B. Would you put b here? Why? Because, I have also this one is x, y. So what do you put here? B divided by 2. Perfect. Then it's not finished, so this one is fixed, these two terms, right? Then I have Cx. Okay, so my vector is this one, x and y. So I need to have a row vector such that, it makes a scalar, so I need to have inner product. So I have a C multiplied by x, and then I need to put a 0 here. Okay. And then the scalar term, which is 1. So the quadratic form, if I call it, this one as t, so theta transpose, this one might be R, this one might be is now theta, and this one is P transpose, this is theta plus 1. Okay? So if I need to find, what is the minimum, and then I need to compute the gradient with respect to the vector theta of the quadratic form that depends on x and y. Okay. But I do it in a compact way. And this one is 2 times r theta, and then plus p equals 0. Okay, because I want to calculate the minimum. Then I get the theta. Theta corresponds to the max or min is equal to minus p r to the minus 1 times p divided by 2. Okay? Then you compute the inverse and then you get it. Now, define what is a positive definite quadratic form. A positive definite quadratic form, okay, is a quadratic form that is all positive except when the arguments are 0. Okay, so since I don't know what is A, B, and C, so I cannot say more than that. So what is here is a definition. I ask you for a definition. Find the minimum. Okay, we did it, of the maximum. Okay, of fxy, and find its value at the minimum. Sometimes this is strange, but you don't do it. And I did the exam 3 hours ago, and we were close to finish, but when I asked her to calculate the value of the minimum, nothing. Now the problem was not so easy like this, so I have domesticated the problem in such a way that it's easy, so it's straightforward now. So if I ask you, what is the value of the minimum? So what I saw, imagine it's a positive definite, so let me use this parabola. So what I ask you is, how much is this? What is the value at the minimum? Okay? If I ask you, I have a one-dimensional function, and I ask you, can you tell me the value at the minimum? So what do? You calculate the position of the minimum, then you plug the solution into the problem, then you get the value of the minimum, right? Okay? So let's make it, and then we go to have a coffee. Okay, so let's make it. So I take this one, this value, and I plug where? Here, here, there, right? Okay, so let's do together. So f theta min is equal to, now let me plug in, so it is minus r to the minus 1p. So that one is minus 1 half, it is r to the minus 1p multiplied by r multiplied by r to the minus 1p. Then this one is multiplied by minus 1 half. Plus, okay, this one is theta min. Plus, now let's go, is P transpose theta. So I just plug into theta the value. So it is P transpose, and then it's that one. So it is P plus P transpose, then it's a theta. So it is minus 1 half r to the minus 1 times P.
Transpose.
The first statement should be transpose, I think.
Oh, because I forgot. Thanks. Okay. And then I have a plus 1. Okay? So, I continue. And then minus minus goes to plus, so it is 1/4. Then I have, as he pointed out, it is p to the minus 1. Okay? And p transpose. Okay? Then I have r to the minus 1 transpose. Then I have r. Then I have r to the minus 1. Then I have p. And then I have minus 1 half p transpose r to the minus 1 p. Now, this one is identity. Okay. Now, what about r to the minus 1 transpose? Now, I can write in a compact way as r to the minus transpose. But, if the matrix is symmetric, the inverse is symmetric as well. Okay? So, if r is symmetric, symmetric means r transpose equal to r, then r to the minus 1 is symmetric. So for this reason, I can write that it is symmetric. So r to the minus transpose is equal to r to the minus 1. So I plug in, and then because of this, it is equal to, so it is 1/4, it is p transpose r to the minus 1 p, and then it is minus 1/2 p transpose r to the minus 1 p. Okay? So what's happened? It is, it is minus 1/4 p transpose r to the minus 1 p.
Plus 1.
Plus 1. I forgot plus 1. Okay. So that's the solution. 1 minus 1/4. Okay? That's the request. Now, these exercises, is it clear? These exercises, I took these exercises from the early exam, because some time ago, a few years ago, the course was attended by just 10 students or so. So it was very easy for the students to make the oral exams only. And so for this reason, I assigned these, kind of very easy exercises as just a go-no-go test to attend the oral, okay? To make the oral. It was 15, 12 students or so, okay? So, just to scratch a little bit. Now, we continue after, with the deterministic random variable and deterministic random variable, okay? And this is another go-no-go. And these 3 exercises that I plan to do. I mean, as usually, I take this and upload, okay? You have already uploaded of the revised part on the Z-transform, and I will upload this new part into the handwritten folder. Okay? I took more than I thought.